A total chemical analysis of a soil may be of little significance as far as the supply of nutrients to the plant growth. Though most of the minerals in the soil are plant nutrients, their uptake by the plants depend on various factors. For these reasons, the discussion of soil chemistry focuses on ion exchange reactions, solubility, and mineral and biochemical transformations. Weathering of minerals and decomposition of organic matter supply ions to the ion pool of the soil solution. Ions are lost from the pool by plant uptake and leaching. Some ions precipitate and some ions form secondary minerals, especially clay minerals, and are subject to dissolution. Clay colloid particles have negative charges. Cations are attracted to the clay particles. The cations are the positive charges. One can remember it by saying cat has paws. These cations are held on the clay surfaces electrostatically. They are held by small particles of clay and organic matter. These small particles are also called microcell or micelle. The cations that can be replaced on exchange site by other cations are called exchangeable cations. They are weakly held and are in direct contact with the soil solution. They can be exchanged fairly easily. Ions that are held very lightly with the colloid may be trapped between layers of clay micelle. They do not pass to the soil solution very easily. They are called non-exchangeable cations. Ion exchange reactions. The ion exchange phenomenon was first identified by Harry Stephen Thomson in England during 1850. When soil was leached or washed with ammonium sulphate, calcium sulphate was detected in the leachate. The ammonium ion in the solution replaced calcium in the soil. Ammonium sulphate plus soil calcium, soil nitrate plus calcium sulphate. The process by which ions are exchanged between solid and liquid phases and or between solid phases if in close contact with each other is called ion exchange. The common exchangeable cations are calcium, magnesium, hydrogen, potassium, ammonium, and sodium ions. The common anions are sulphate, chloride, phosphate, and nitrate ions. Cation exchange. Cation exchange capacity is defined as the amount of positive charge that can be exchanged per mass of soil. The unit of cation exchange capacity CEC are milliequivalents per 100 grams represented by MEQ over 100 grams or centimoles charge per kg represented by CMOLC per kg. Cation exchange capacity or CEC is a measure of how many cations can be retained on soil particle surfaces. Negative charges on the surfaces of soil particles bind positively charged atoms or molecules, cations, but allow these to exchange with other cations in the surrounding soil water. This is one of the ways that solid materials in soil alter the chemistry of the soil water. CEC affects many aspects of soil chemistry and is used as a measure of soil fertility, as it indicates the capacity of the soil to retain several nutrients, for example, potassium, nitrate, calcium ions in plant available form. It also indicates the capacity to retain pollutant cations like lead. CEC is measured in moles of electric charge. So, a cation exchange capacity of 10 cmolC per kg could hold 10 cmol of sodium cations with 1 unit of charge per cation per kilogram of soil, but only 5 cmol calcium ion, that is 2 units of charge per cation. Cation exchange capacity arises from various negative charges on soil particle surfaces, especially those of clay minerals and soil organic matter. Phyllosilicate clay consists of layered sheets of aluminum and silicon oxides. The replacement of aluminum or silicon atoms by other elements with lower charge, example, aluminum replaced by magnesium ion, can give the clay structure a net negative charge. This charge does not involve deprotonation and is therefore pH independent and called permanent charge. In addition, the edges of these sheets expose many acidic hydroxyl groups that are deprotonated to leave negative charges at the pH levels in many soils. Organic matter also makes a very significant contribution to cation exchange due to its large number of charged functional groups. CEC is typically higher near the soil surface where organic matter content is highest and declines with depth. The CEC of organic matter is highly pH dependent. Cations are adsorbed to soil surfaces by the electrostatic interaction between their positive charge and the negative charge of the surface, but they retain a shell of water molecules and do not form direct chemical bonds with the surface. Exchangeable cations thus form part of the diffuse layer above the charged surface. The binding is relatively weak and a cation can easily be displaced from the surface by other cations from the surrounding solution. Measurement of CEC. Cation exchange capacity is measured by displacing all the bound cations with a concentrated solution of another cation and then measuring either the displaced cations or the amount of added cation that is retained. Barium Ba2+ and ammonium NH4+ are frequently used as exchanger cations, although many other methods are available. CEC measurements depend on pH and therefore are often made with a buffer solution at a particular pH value. If this pH differs from the natural pH of the soil, the measurement will not reflect the true CEC under normal conditions. Such CEC measurements are called potential CEC. Alternatively, measurement at the native soil pH is termed effective CEC, which more closely reflects the real value but can make direct comparison between soils more difficult. Anion exchange. The process of anion exchange is similar to that of cation exchange. Under certain conditions, hydrous oxides of iron and aluminium show evidence of having positive charges on their crystal surfaces. The positive charge of colloids are due to the addition of hydrogen ion in hydroxyl group, resulted in net positive charge, that is OH2 plus. This positive charge will attract anions with negative charge. In contrast to CEC, AEC is the degree to which a soil can absorb and exchange anions. The pH of most productive soils is usually too high. Exceptions are for volcanic soils. For full development of AEC, and thus it generally plays a minor role in supplying plants with anions. The capacity for holding anions increases with the increase in acidity. The lower the pH, the greater is the adsorption. All anions are not adsorbed equally readily. Some anions, such as H2PO4, are adsorbed very quickly at all pH values in the acid as well as in the alkaline range. Chlorine and sulfate ions are adsorbed slightly at low pH, but none at neutral soil, while nitrate ions are not adsorbed at all. Hence, at the pH commonly prevailing in the cultivated soils with nitrate, chloride and sulfate ions are easily lost by leaching. In general, the relative order of anion exchange is hydroxyl, represented by OH greater than H2PO4 greater than sulfate SO4 greater than nitrate NO3. Importance of anion exchange. The phenomenon of anion exchange assumes importance in relation to phosphate ions and their fixation. The exchange is brought about mainly by the replacement of hydroxyl ions, that is OH ions of the clay mineral. The adsorption of phosphate ions by clay particles from soil solution reduces its availability to the plants. This is known as phosphate fixation. As the reaction is reversible, the phosphate ions are again available when they are replaced by hydroxyl ions released by substances like lime applied to the soil to correct soil acidity. Hence, the fixation is temporary. The whole of the phosphate adsorbed by clay is, however, not exchangeable, as even at pH 7.0 and above. So, substantial quantities of phosphate ions are still retained by clay particles. The hydroxyl ions originate not only from silicate clay minerals, but also from hydrous oxides of iron and aluminium present in the soil. The phosphate ions therefore react with the hydrous oxides also and get fixed, as in the case of silicate clay, forming insoluble hydroxyphosphates of iron and aluminium. Base saturation. The proportion of CEC satisfied by basic cations like calcium, magnesium, potassium and sodium is termed percentage base saturation, that is BS percentage. This property is inversely related to the soil acidity. As the BS percentage increases, the pH increases. The availability of nutrient cations such as calcium, magnesium and potassium to plants increase with increasing BS percentage. Base saturation is usually close to 100% in arid region soils. Base saturation below 100% indicates that part of the CEC is occupied by hydrogen and or aluminum ions. Base saturation above 100% indicates the presence of soluble salts or lime. Soil reaction or pH. Definition: pH is the potential hydrogen. Soil pH is a measure of the acidity or basicity of a soil. pH is defined as the negative logarithm with base 10 of the activity of hydronium ions H plus, or more precisely H3O plus aqueous in a solution. In soils, it is measured in a slurry of soil mixed with water and normally falls between 3 and 10, with 7 being neutral. Acid soils have a pH below 7 and alkaline soils have a pH above 7. Ultra acidic soils pH less than 3.5 and very strongly alkaline soils with pH greater than 9 are rare. Soil pH is considered as a master variable in soils as it affects many chemical processes. It specifically affects plant nutrient availability by controlling the chemical forms of the different nutrients and influencing the chemical reactions they undergo. The optimum pH range for most plants is between 5.5 and 7.5. However, many plants have adopted to thrive at pH values outside this range. Determination of soil pH. Soil pH is commonly determined by mixing 1 part of soil with 2 parts of distilled water or neutral salt solution. Occasional mixing over a period of 30 minutes to allow soil and water to approach an equilibrium condition, and measuring the pH of the soil water suspension using a pH meter. A rapid method is by using pH indicator dye. pH scale. pH scale is a measure of the degree of the acidity or alkalinity of a solution as measured on the pH scale of 0 to 14. The midpoint of 7 on the pH scale represents neutrality, that is, a neutral solution is neither acid nor alkaline. It is important to understand that pH is a measure of intensity and not capacity. The pH scale is logarithmic, which means that moving on unit either way on the pH scale results in an 10-fold increase in the degree of alkalinity or acidity. It also gives the universal color indications from red to purple, neutral being green. Factors affecting soil pH. Inherent factors affecting soil pH such as climate, mineral content, and soil texture cannot be changed. Natural soil pH reflects the combined effects of soil forming factors like parent material, time, relief or topography, climate, and organisms. The pH of newly formed soils is determined by minerals in the soil's parent material. Temperature and rainfall control leaching intensity and soil mineral weathering. In warm, humid environments, soil pH decreases over time in a process called soil acidification due to leaching from high amounts of rainfall. In dry climates, however, soil weathering and leaching are less intense and pH can be neutral or alkaline. Buffering capacity. Buffer capacity, represented by beta, is defined as the moles of an acid or base necessary to change the pH of a solution by 1 divided by the pH change and the volume of buffer in liters. It is unitless number. A buffer resists changes in pH due to the addition of an acid or base through consumption of the buffer. It quantifies the ability of a solution to resist changes in pH by either absorbing or desorbing hydrogen or hydroxyl ions. When an acid or base is added to a buffer system, the effect on pH change can be large or small depending on both the initial pH and the capacity of the buffer to resist change in pH. Signification of pH. pH affects nutrient, minerals and growth. The effect of soil pH is great on the solubility of minerals or nutrients. 14 of the 17 essential plant nutrients are obtained from the soil. Before a nutrient can be used by plants, it must be dissolved in the soil solution. Most minerals and nutrients are more soluble or available in acid soils than in neutral or slightly alkaline soils. Phosphorus is never readily soluble in the soil, but is most available in soil with a pH range centered around 6.5. Extremely and strongly acidic soils in the range 4.0 to 5.0 pH can have high concentrations of soluble aluminum, iron and manganese, which may be toxic to the growth of some plants. A pH range of approximately 6 to 7 promotes the most ready availability of plant nutrients. Soil electrical conductivity. Electrical conductivity (EC) is the ability of a material to transmit or conduct an electrical current and is commonly expressed in units of millisiemens per meter or decisiemens per meter, which is equal to the reading in ms over m divided by 100. Factors affecting EC. Soil moisture. The electrical conductivity of soil varies depending on the amount of moisture held by the soil particles. Sands have a low conductivity, silts have a medium conductivity, and clays have high conductivity. Consequently, EC correlates strongly to soil particle and texture. In addition to EC values, Separating variations in the soil texture, EC has shown to relate closely to other soil properties used to determine a field's productivity. Water holding capacity and drainage. Droughty areas typically have distinct textural differences from those with excess water. These can be identified using EC. Since water holding capacity typically has the single greatest effect on crop yield, this is likely the most valuable use of EC measurements. Cation exchange capacity CEC. CEC is related to percent of clay and organic matter represented by OM. As the percent of clay and organic matter increase, the CEC also increases. Depth to clay pan or rock outcropping. The response of conductivity to the presence of clay has been used to accurately predict the depth of topsoil over a clay layer or rock outcropping. Porosity. The greater the total soil porosity, the more easily it conducts electricity. Soil with a high clay content has more total pore space than sandier soils when other soil parameters remain constant. Salinity. An excess of dissolved salts in the soil is readily detected by electrical conductivity. Temperature. As temperature decreases to the freezing point of water, soil EC decreases slightly. Below freezing, soil pores become increasingly insulated from each other and overall soil EC declines rapidly. Significance of EC. The EC of the soil has direct relationship with growth of different crops. Rating chart of soil EC where less than 1 ds per meter is normal, 1 to 2 ds per meter critical for germination, 2 to 3 ds per meter critical for salt sensitive crops, greater than 3.0 ds per meter injurious to most of the crops. Summary. The ion exchange in soil is due to the presence of residual positive and negative charges on the soil colloids. These residual charges result due to the process of isomorphous substitution and ionization of hydrogen and hydroxide functional groups. The negative charges attract positively charged ions and the positive charges attract negatively charged ions from the soil solutions coming in contact with the colloids. The ions thus attracted are reversible and are on equivalent proportions. Exchange of cation is called cation exchange and exchange of anion is called anion exchange.